Guten Morgen, everyone. I see some familiar faces in the audience. That's awesome. To all the new ones, let's catch up afterwards if you're interested in that. I hope everyone had a good night's sleep because today we are going to talk about memory management in Flutter. My name is Raitis. I'm a mobile iOS and Flutter developer at Chili Labs. I have created two Flutter apps myself, Kitchenette and OrbitGuard. OrbitGuard is the latest one, and I played around with Flame Game Engine for that one. If you haven't checked it out already, please do. Share your feedback and help me make this game go viral. I'll share the links after the talk, so if you're interested, just don't go anywhere, at least not yet. Mostly I play basketball. Are there any basketball fans in attendance? Nice. Any of you are fans of Boston Celtics as well? Let's talk basketball afterwards. Just come find me. I've been also doing kickboxing for quite some time now, so be careful around me. I'm just kidding. Don't take me that seriously. Let's connect on any of the social media platforms, for example, Twitter. I'm not very active over there in terms of tweeting stuff, but I'm trying to improve daily. We'll see how it goes. All right. Today we are going to talk about what are some early signs and tells that your app is leaking a memory. What exactly is a memory leak and what characteristics does it possess? And what is the role of objects and references inside our apps? Also, how memory is being allocated and deallocated in Flutter. How can we find the source of the leak and fix it afterwards? And also, we'll take a look if there are some memory optimization techniques that we could use to potentially prevent memory leaks in our applications. All right, please raise your hand if you have ever noticed like deterioration of your app's performance by experiencing some noticeable frame drops or app freezes. Wow, that's a lot. And what about app crashes, especially the ones with the out of memory error in case of debugging the app? And let's just add increased battery consumption to the list as well, because sometimes our app just uses more computational power than it's actually necessary. And if you have experienced, I think almost all of you raise your hand. So if you have experienced any of these symptoms, the chances are that your app was actually leaking memory. What exactly is a memory leak? It's a condition when when our application doesn't release the memory that was so I'll start over. So when application doesn't release the memory that was previously allocated for some object and it's not used anymore. And it can lead to unwanted gradual increases in memory consumption, causing app just to work slower and just worse in general. Was the explanation like clear enough? Can you? All right. So where was I? So can you raise your hand if the explanation of what exactly memory leak is wasn't clear enough?
It was.
All right. No hands at all. Like I don't believe you. Let's just try. Let's just try something a bit more practical. Can you like put your hands in front of you like this, all of you, and now just clap, but keep your hands together. Memory gets allocated. Now release your hands. Memory gets deallocated. Clap again. And this is where memory leak happens. You can release your hands, by the way, now. And yeah, so it's essential for every application to have like proper memory management to ensure that everything works well together. let's not confuse memory leak with memory bloat, because memory bloat is something that whenever too much memory gets used for something. For example, if we are loading too much data into the application, like a large image, and never releasing it afterwards. So to sum it up, memory leak is a gradual increase in memory consumption over some period of time. Memory bloat is a sudden, rapid increase in memory consumption, and then it just plateaus. When talking about objects, we can we can separate out Dart-specific objects and Flutter objects. In Dart, everything is an object, from string, boolean, double, to lists, maps, sets, and so on. Everything apart from null. The difference between Dart objects and Flutter objects is that Flutter objects come with their own unique set of characteristics. For example, widget, which is immutable, but it can be associated with other objects like state object, which in fact is mutable, and it also comes with its own lifecycle methods. So just as an example, and based on their lifespan within the app, we can distinguish short-lived objects and long-lived objects. Short-lived objects are objects that are created and destroyed frequently throughout the execution of the app, and most of the time they are local variables defined within the scope of the functions, iterators. Also, they can be widgets and so on. Long-lived objects, on the other hand, are much less often garbage collected, if at all, during the execution of the app. And most of the time they are global variables, controllers, even cached objects, and so on. All right, let's take a quick look at how objects are referenced within our apps. So with every Dart application, a root object gets created, and it references every other object that gets allocated into the memory. And those objects, references that are being held between the objects form a retaining path. And retaining path basically is a sequence of basically a sequence of one or more references pointing from root to an object, and it retains the memory, meaning that it cannot be garbage collected because the object is considered to be reachable when the object has at least one retaining path. It can have multiple, by the way. And it becomes unreachable once all of those references are removed from the object and it's not considered to be in use anymore, and it is eligible for garbage collection. Right. I'll just leave it open so it's easier. All right. Memory allocation. So memory allocation is a process of assigning portions of virtual memory for an executable program. In other words, every application needs memory to be able to operate, to execute commands, do some calculations, store and manage also some data. When talking about memory allocation, we can distinguish two types of memory allocation: static memory allocation and dynamic. Static memory allocation is something that happens during the compile time, and what it means is that objects that are being allocated are of fixed size, and that means that they cannot be changed during the runtime. Their size must be known before the runtime, during the compile time, and usually constants and static variables are the ones that are allocated statically. Dynamic allocation, however, happens during the runtime, and it sort of adds flexibility in terms of memory allocation and size, because objects are allocated only when it's required by the application, not earlier than that. And also, objects that are allocated dynamically are stored in a memory space called Dart heap. Dart heap, yes, and it's operated by the operating system, meaning that its size is limited to the size of virtual memory. And whenever overflow happens within the heap, memory leak occurs. And also, the heap is managed by a Dart virtual machine, meaning that memory is assigned on the object creation and it's released when object is no longer of use. And since Dart is a garbage collected language, its runtime comes with its own garbage collector, and its main task is to identify which objects are no longer reachable, reclaim the memory from them, and keep it available for any future allocations. And Dart garbage collector, being the automatic memory manager, means that us developers, we don't really need to perform memory management tasks ourselves, at least not in a traditional sense. Like, we don't need to write code to perform those memory management tasks that garbage collector does for us. And basically, we can look at the garbage collector as our trusty sidekick, as the behind the scenes hero that always has our back and always, well, almost always cleans up after us. And if you're interested in knowing more about how exactly the garbage collection works, I highly recommend checking out this talk by Anna Lushenko. It's very well explained, very detailed, and very well illustrated. So if you're interested, please check it out. It's really good. All right, I guess we have finally arrived. I'll share with you what I do to, like how I track memory leaks and what I do to find them. And I'm using tools provided by Flutter and Dart teams, specifically Flutter DevTools Memory View in combination with Leak Tracker package. I use them both together because, in my opinion, like, I can get the most out of them if I use them together. Exactly. All right. White Ninja says that we need to do something. I guess we can do something. Whoops. You weren't supposed to see that. All right. I have created a small sample app that leaks a little bit of memory. I don't think we need to see this. And application itself is very simple. It consists basically of 3 widgets: a leaking container, the green one. Yeah, the green one. And underneath it instantiates text editing controller that is never disposed of. Red button, toggle container, removes the leaking container from the widget tree and inserts it back in. And the blue button populates a list of objects that are stored. The list is stored inside the singleton object, and every time we press a button, we are populating it with a million objects. And we have also opened up Flutter DevTools, and what we are interested in is specifically memory view. Yeah, one thing to mention is usually if you want to get the most accurate readings about memory consumption in your app, you should run the app in profile mode. For the purpose of this demo, I'm running it in debug mode. It's because of the full out-of-the-box support for leak trackers package. It's fully supported out of the box in debug mode. And if I'm not mistaken, then tracing instances also is currently working only in debug mode. And what we see here is a live memory chart of current memory consumption. For example, what we see here is this orange dashed line. It's a resident set size. It's basically the memory that is currently loaded into the RAM, and it's available for immediate use. Also, this blue wave thingy, it's currently consumed like Dart and Flutter size of the currently consumed Dart and Flutter memory. Also, we will see these blue dots. Those are garbage collection events triggered by virtual machine. We could also do it manually. As you can see, the blue circle indicates that it's triggered by us. And what we'll do now is we will switch to Detect Leaks tab. So if you have ever opened DevTools memory view, you know that this tab doesn't appear by default. You have to use the leak trackers package and enable memory leak tracking specifically within your app. And what it does, it tracks the how many memory leaks your app has. And the most common leak types: not disposed, not garbage collected, and garbage collected late. So let's try to create some leaks. And as you can see, something is leaking. And we have 3 memory leaks. All of them are not disposed. What we can do now is press this Analyze and Download button and open it up. And what we will see here is basically a full stack trace of our leak. So as you can see, here's the type, not disposed, total count 3, object in question, text editing controller, as I mentioned earlier. And since my sample app is pretty small, I can already notice a familiar class name, leaking rectangle widget state, specifically the init state method. And this is where the text editing controller gets instantiated. And what we can do now with this information is investigate further, go to the code, go into the code and understand if we are or we are not disposing of the object. We won't do it today for the purposes of the demo. Instead, we will switch to Profile Memory View, Profile Memory tab. And what we are looking for here is unusual amount of instances created and the total size. Let's try to generate some leak objects. And as you can see, we have now like 6 million leak objects, and their total size is over 90 megabytes. And if we hover over, we can see that this is a project class, meaning that it's created by yours truly. And with this information, like we now have a suspect. And with this information, we can go to Trace Instances tab. And then we can filter it out. Leak object. Yeah, we can check the checkbox, say that we want to trace it and select it. And we also need to generate some sample so something can be collected. And if we refresh it, we should be able to see something. Yes, exactly. So this is a call tree. This is from the bottom up. You could also expand it and see like just a regular call tree. So this would be the last method. Yeah, and also this indicates that this is where the objects are being generated from, specifically the private method of the main page state class on increase leaking object. And again, with this information, we could now dig into our code and go further. Also, as you can see, the consumed memory grew significantly. So that's about it for the demo. Obviously, I came prepared in case of any issues. Some might even say over-prepared, but it is what it is. All right, the fix for the commonly tracked leak types is fairly simple if you have successfully located the source of the leak. For objects that were not disposed but were garbage collected, all you need to do is call the dispose method on the object. For example, in Stateful Widget's dispose method. This method can also be close or cancel on different objects, like subscriptions or string controllers. For objects that were disposed but not garbage collected, or they were garbage collected later than they should have been, you need to assign reachable objects reference to null right after disposing of the object. But one very hard leak pattern to catch is related to storing large short-living objects within the context of closure. And if you look at the example on the screen, on the left side, we are storing the entire build context object in the closure, and that in a handler, and that handler is used somewhere else, and this could potentially cause a memory leak depending on how the handler is used, because in this case the closure can actually outlive the widget. And what we can do is we can instead create a single object of theme context, and so it can be shared across all build context instances, and we can instead use the result of it inside the closure. And this is recommended approach from the documentation as well. So if you're not doing it already, I think you should. All right, let's take a look at some of the optimization techniques that we could use. Not all of them. So this is just to get the ball rolling, so you can come up with your own solutions as well. If you're coming from iOS native background, you already know about weak references. In Dart and Flutter, we also have this. We could use weak reference class. It basically creates a reference that doesn't prevent the object from being garbage collected, meaning that it can be garbage collected at any time. And how it works, we just wrap our object within a weak reference class and use it as a regular object, except that we need to perform some additional safety checks, because the target of the weak reference can be null. We can also lazily initialize our objects. For example, using factory constructors, getters, also late initializers. All of these boil down to the fact that they are initialized only when it's necessary, and only a single instance of object gets created. Why not use mixins? I mean, if you're dealing with a lot of, let's say, text editing controllers within your screens, within the app, why not somewhat extract that logic of disposing the object to a mixin instead of doing it manually? It can just get very cumbersome really quickly, and you might even forget to do it. But again, this depends completely on how your app is structured, or all the implementations. So maybe this doesn't even make sense to look at this. So I would say it depends, but in my opinion, this is the one you can get creative with the most. And talking about discarding resources, don't forget to dispose of your objects within the dispose method of stateful widget. Yes, it's manual work, but it's highly effective. You just need to stay aware of it and to not forget to do it. You could also set up lint rules. If you're not doing it already, my question to you is why? Because first of all, not only you can write cleaner code, cleaner syntax with setting up lint rules, but it's also super easy to do. And we are using rules provided by Dart in combination with Dart code metrics, ensuring that all of our objects are properly disposed, all of our subscriptions are canceled, and things are closed. So I highly recommend this one. Using const constructor whenever possible. Why? Well, because first of all, it's a recommended optimization, and secondly, it's also a performance gain. And when we are creating an object, let's say we are creating two identical objects with the same const constructor, only one object actually will be created, and any subsequent objects created with the same const constructor actually will reference the first one, the one that was initially created. All right, let's take a look at these two examples. On the left, your left, we are using pure Dart, and on the right, we are using Flutter widgets. So, test for you. Raise your hand if you think in the example on your left, speaker 1 and speaker 2 are identical. So, test for you. What do you think? I can repeat the question. So, if you think objects speaker 1 and speaker 2 are identical, raise your hand. All right, not that many hands, but I expected a bit more. I mean, using the identical method that compares the objects. Yeah, it will print just true or false. Okay, I'll just some of you raised your hands previously, so you passed the test. They are indeed identical. And the same question for the example on the right with Flutter widgets. Raise your hand again if you think box 1 is identical to box 2, if it will print true. Raise your hand. Dun, dun, dun. False. So some of you are probably like, what is this guy on about? They're like, literally the same object. Just look at the code. Like, it's the same. How can it be? So the thing is that the constant canonicalization for widgets in debug mode happens differently than it does in release mode. And this is because of the added support for debugging tools in debug mode. And in release mode, it will actually return true. But you don't have to worry because in debug mode, the widget canonicalization is still performant enough. It happens in well enough, so you get the most performance benefits out of it. And regarding regular constant constructors, like the non-widget ones, they work the same in debug and release modes. All right, let's quickly recap what we talked about today. So memory leak happens whenever our application fails to release memory that is unused anymore and make it available for any future allocations. A reachable object is an object that has at least one reference pointing to it, meaning that it cannot be garbage collected because it's still considered to be in use by the application, even if it isn't. Unreachable object is whenever references from our reachable object are removed, then it becomes unreachable and it can be garbage collected. We can detect the source of the leak by using tools provided by Flutter and Dart teams, specifically their tools Memory View in combination with Leak Tracker package. And what can we do to prevent memory leaks potentially? We could use some memory optimization techniques like using weak references, disposing of resources within the dispose method of stateful widget, setting up lint rules, and using const constructors whenever and wherever we can, and of course others. Dankeschön for listening. I hope you enjoyed. You were an amazing audience. Hopefully this is not my last talk. And yeah, if you have any questions, you can ask them. If not, we can connect afterwards. Just talk live, talk basketball, Boston Celtics, let's go. And yeah, you can check out my apps if you want to. I recommend checking out the Orbit Guard game. Yeah, thank you again.